Okay, so let's assume, so this is going to be the third lecture by Claudio Polini.
Okay, thank you very much. So I'm gonna, as I told you today, I'm gonna do the rank of the modular differentials. So first of all, I wanted to write up here the two things we saw last time, which are very important. As I told you, in fact, they will come up in the proof today. One is the relative cotangent sequence that we have all the time. We have rings in this way. So B is an A algebra, R is a B algebra, and is also an A algebra. So you have this sequence, and the conormal sequence that is an application of actually the cotangent sequence in the case when you have A, R, and the quotient of R, T. And then you prove that this is the cotangent sequence, okay? And remember that this is split injective, so it's exact if phi, the natural math, has a right inverse. And we're going to use this thing today when we compute the rank of the modular differential. So first of all, as I said last time, now we definitely need to assume characteristic of K0. You could do this in more generality, but this part would become much more complicated. So, so as I said, the goal is this, and what we're going to show also the following, which will be interesting, will come as a side of the proof, that if you have two fields and this extension is finitely generated, okay, then the extension is algebraic if and only if the modular differential of K over K is 0. So it gives you a way to characterize exactly when an extension is algebraic using the modular differential. Okay? So, and this will be a side thing that will come obviously in the proof. And now, to start, I have to recall the definition of transcendent degree. Oh, how do I spell it? Tran. And to talk about transcendence degree, we have to talk about transcendence basis. And obviously, I will not give most of the proof because the proof are exactly the same that you did for linear algebra, for vector spaces, and for bases. So it will not be so much of a proof, more a reminder, and you can try to prove it at home. It's exactly the same proof as you see. So let me first give the definition of what actually a transcendent basis is. A subset U of the field K is a transcendent basis I never spelled this correctly, so okay, of K over little k if, so I'm going to make a picture like I always do in Galois theory. So you have K here, you have K of U, this field in the middle, and K. And what you want is that this extension, okay, is algebraic, and this is purely transcendental, okay? So this extension should be algebraic, and this should be purely transcendental. Okay, so let me write it down here. So if U is algebraically independent over K, and the extension from Ku to K is algebraic. So this is the definition of transcendent basis. And what is the transcendent degree? That we are going to prove that the number of elements of the transcendent basis does not depend on the U you choose, but only depend on the extension, okay, on the field extension. Yes?
Sorry, one question about, actually, before the conormal sequence.
Yes?
So last time we proved that phi has a right inverse, if only if, like, gamma has a left inverse, correct?
Delta.
Delta, sì.
So in particular is exact.
Oh, okay.
Yes. So now, as I said, so what's going to be the transcendent degree? We are going to prove that this transcendent basis does not depend on the U you're choosing. Every transcendent basis has the same number of elements, exactly like a basis of a vector space, and then this number of elements is an invariant that depends only on the field extension, and that invariant we call it the transcendent degree. So let's try to prove that, and the proof is the same, as I said, that you do for vector spaces, so I'm going to just state it, is, effect from field theory, let me call it proposition, but it's really something of a recall. So you have the first part, you remember what you do when you teach even linear algebra. You want to take two sets. One is a generating set, the other is a linearly independent set, and you want to prove that in the middle you can find a basis, okay? That you can always build a basis in the middle. So this is going to say exactly the same thing. So it says you have V containing W, okay, and they could be empty, but subsets of K, okay? And so that what you want is that W, okay, so actually let me write it like this. V is algebraically independent. Over little k. So this tells me these are the linearly independent elements, okay? And the other one, I want it to be generating. So how do I say generating? I just say that the field generated by W, KW, the extension from KW to big K is algebraic, okay? So, and this field extension, big K, is algebraic. So this tells me that W generates and U is linearly independent. Then the claim is there exists a set in the middle, a transcendental basis, I call it big U, and this would be of K over K that sits in the middle. So you just have to keep adding element of W to U until, like you do in a field theory, until you reach the position you want. So the second one is again the same step you use to prove it, the number. What do? We have, that doesn't depend. The number doesn't depend. You have two bases. You take an element of one and you switch it with an element of the other, so that you can switch elements. This shows that the number of elements are the same. So you have two transcendental bases, U and U prime, okay? Now the bases should be plural because there are two of K over K. So here there is an E, not an I. Okay? Then for every U prime in U prime, okay, there exists a U in U, so that if I take off U to U prime, okay, so I take U prime and I take off my U prime to it, and instead I add my U, okay, this is still a transcendental basis. Okay, of K over K. And then immediately as a corollary of these two, you get that any transcendent basis of K over K have the same cardinality. So the cardinality is an invariant, and so we call this cardinality the transcendent degree. So every field extension has a transcendent basis. It follows immediately. And the number of elements, the cardinality, of such bases is an invariant of the extension, and we call it the transcendent degree. Okay, so this is our invariant. And remember what I told you in the preview, our point is to prove that that's exactly the rank of the modular differential of big K over the small k. Okay? So, first of all, before I do that, a simple corollary that will be useful is what happens if I have a tower of fields. So you have a tower of fields, one containing the other, and you have a transcendent basis here, for example, and a transcendent basis here. So what can you say about the transcendent basis here? Well, it's clear, it's just a union of these two. You can show that the field that, so this implies these are transcendent bases. This implies that this thing is algebraic. And this is, fully transcendental. Which implies union V. How do I write it good, but you can see that this union, they look just to you, but U union V is a transcendent basis. So this gives us the corollary, and the statement of the corollary is what you imagine. The transcendent degree of L small k is just the sum. So it's not the product, it's the sum. Okay? So it's the sum of the transcendent degree. And the proof is sketched here, you can go through the detail, but that's really the idea. Okay, now I'm going to go to, I need a lemma before I can actually prove what I want, that this is the rank of the modular differential. So let's start with the lemma. I hope you remember this because now unfortunately I erased it. So I hope that this concept is clear. And let me take a second so you can think. So this is the definition of transcendent degree, which is what we need. Okay? Just the cardinality of the transcendent basis. So remember, think of a transcendent basis as a way to split a field extension in two pieces. One that is algebraic and one that is purely transcendental. So think about it this way. Okay? So the first lemma that allows us to prove the main theorem says as follows. If you have, again, a tower field like there, and you assume that this part is algebraic, okay, then the modular differential of k over k is tensor with L over big K. This is a big K vector space, okay? And that is also a big K vector space. Okay, I tensor over it. This, guys, is isomorphic to this. So this becomes an L vector space, okay? And now it's exactly this L vector space. This should remind you of something. What should it remind you? Of the cotangent sequence. So we are going to use the cotangent sequence. Okay? It's clear from here that we have to use somehow the cotangent sequence. But actually it's not really, I'll do it simpler than that. I won't use the cotangent sequence. I'll use it in the theorem. But I'll do it differently. So one thing, this extension, I don't assume anything, only that this is algebraic. So they're not finite, okay? So I want to reduce to the finite case, okay? So I write L as a union of Li where each, these are finite algebraic. And this is actually, could be infinite, obviously infinite union, but you can do it nesting. So this is a direct limit. Okay? And when I do that, remember what we said. You had an homework that told you that taking direct limit is compatible with taking differential. So we may replace since direct limit is compatible with taking differential, we may assume, so to pass to the modular differential, yes?
Can you read the subscript on that first omega? Is that a little k?
This is the little k, and this is the big K and the little k, and this is the big L and the little k.
Okay, thank you.
Okay? Okay, so we may replace Li by L, so L by Li, to assume that the extension is finite. Is finite algebraic. Can anybody tell me what's special about an extension be finite algebraic in characteristic 0? Anybody? If you have a finite extension, algebraic in characteristic 0, what do you know?
It's simple.
It's simple, because remember we are separable, so it's simple. So it's just generated by one guy. So now we know that L is simply, okay, K of X over F of X. Okay? By the primitive element theorem. So you can write it this way. Why can I, and not only because it's separable, the first derivative is 0. Okay? That's also important. You take little x, little x is the guy, so let's say that this is k, this should be a big X. And then let's say that this is, no, let's not call it big, let's call it epsilon. Okay, this f prime of epsilon is different from 0. F of epsilon is 0, but f prime of epsilon is different from 0. Okay, so far so good. Okay, so this is just a primitive element theorem. Now, what's happened? Why did I like to write it like this? Because I have this theorem that tells me what to do on the modular. I know very well the modular differential of a polynomial ring, and I know the modular differential of a quotient. So let's write it down. The modular differential of L over small k is, I'm gonna first write the modular differential of L over k, actually. You could do a step at a time, it would be useful. I shouldn't do it maybe like this, like I'm doing it, but it's okay, it's a little faster. So first, I take the modular differential of big K over K, and I tensor it. And then I still have to take the direct sum of L dx, this x. Okay? Actually, little x is really the image, if you want. I should not call it epsilon, because that would be epsilon. Let me call it little x, because then I can call it dx. And this is big K, okay? This is a, let me call it little x, because this is really little x. And then you have to go modulo what? Like I have to go modulo the derivative, remember? I always have to go modulo d of I. So that's f prime, but that's not enough. Why I cannot just go modulo f prime? I also, f is always coefficient in k. And since I'm computing a small differential respect to k, you also have to do the derivative of the coefficient. Okay, chain rule. And so you get something here, all right? But however, that something doesn't matter. Why? Because the point is that this is a unit. Because f prime is different from 0. So this tells us that this part splits this part off. Okay? Because you have an L downstairs and an L upstairs. These are vector spaces. You have an L upstairs and L downstairs. Okay? So this tells me, this is L, if you want, and this tells me that this guy is simply L tensor omega k of big K. Okay? And now we have our claim proven. Okay? So now the proof of the theorem will come immediately and will lead to the corollary right away. Okay? So the proof of the theorem is as following. The theorem will tell you also what I told you before, that its extension is algebraic, the modular differential is 0. So let's see what the theorem says and what's immediately the corollary. So the theorem tells you as following. So you have just this field extension, and then you consider a set U, okay, containing K, and then you consider the differential, call it D of K over K. Okay? And the theorem says U is a transcendental basis, transcendence basis of K over K, if and only if the dxi form a basis of the modular differential. Yes?
That part where you cross it out, can you
Yes.
say what you did again?
So this guy is a unit because it's different from 0. Any element different from 0 is a unit. So this guy is a unit, and so I can simplify. Is this clear? So this part splits off. I mean, you're in vector space. In a vector space, if you have anything, without anything, it goes off, no? Yeah. So now, as I said, this is not the only thing you go modulo, there are other stuff, but as soon as there is, I don't care if this is different from 0, it's 0. As long as there is a unit, this thing blows up, so there is no problem. So now, so transcendence. I didn't finish writing it as usual. So this is a transcendent basis if and only if the dxi, so you take the image of this for the modular differential, is a basis of the modular differential, a k basis, obviously over small k. This is a vector space, okay? Oh, sorry, not small k, it's big K. This is a obviously modular over, big K as well, and this is a k basis of this guy. So if we prove this, you should see immediately that from here you can compute the dimension of K of this vector space, because you have a basis. And this tells you that the dimension is exactly the transcendent degree. Okay? So I get what I want right away. So let's do the proof of the main theorem. So first of all, I have to make a tower field. I told you I do each direction at a time. Actually, it's very funny because once I prove this direction, and then I'm going to use it in the second direction. So be careful. So I prove it this way, okay? I prove this first. So assume that you have a transcendental basis. So what does it mean to have a transcendental basis? It means that you have this K, you have KU, and K, and this is algebraic. Okay? So that's what you care. That's what we get. Okay? And now, we also know, okay, that let me call this K0. If I want to look at the K0 over K, is purely transcendental. So do you remember how purely transcendental extension look like? So let me call it purely transcendental. So how do they look like? K0 is simply K, you add a bunch of variables, and then you localize. Okay? Because it's K round bracket xi. But we know that the modular differential of a polynomial ring is free with basis dxi. And you know that the modular differential localizes. So this tells me immediately, by what we saw, that dxi is a basis of K0. Of the modular differential, is a K0 basis of the modular differential of K0 over K. Okay? Good. But now, so I use this fact. I still did not use that this guy is algebraic. How I'm going to use this? Invoking this lemma. The lemma says since the extension is algebraic, I have this relation among the modular differential. So now, this one tells me that the modular differential of big K over little k is, which is this, is the same as taking the modular differential of K0 over little k and tensor it with big K. So if I have a basis here, it's just an extension. So I'm done. Okay? So this implies that one tensor dxi, and these are the dxi of K0 over K. This is dk0 over K, obviously. But you just tensor with one. This is a K basis of omega. So this proves a part. All right, guys? Okay? Now we're going to prove the converse. You see, I used both parts. This one gave me this, and this part gave me this. I told you, think about the transcendental basis as a way to split off the extension. So the converse. This is a little bit harder, but not so much, but we have to use that part also. So let's see how we do it. We assume that this guy is a basis. So okay? Again, we look at this extension. Why? Because what we want to prove, and we call this K0, we have to show that this is algebraic. Okay? So now, I'm going to use the relative cotangent sequence. That's why I put it up there. So the relative cotangent sequence apply to what? What are my A, B, and R? A, B, and R are, this is big K, this is K0, and this is small k. Okay? So what does it give me if I change a symbol that way? R is big K, it gives me big K tensor over K0 of the modular differential of K0 over little k goes to the modular differential of big K over little k, and this goes to the modular differential of big K over K0. Okay? All right? But now, what we know is that a basis of this guy, because you can use the first part. You remember, Ku generates K0, okay? And a basis of this guy gives me a basis of this. I get a basis of this from a basis of this tensor with K. So this map is surjective by assumption. And star is this. Because the xi were the generator of U. I mean, I don't even care that this dxi form a basis of this. I don't care. The point is that dxi live here. And you tensor with k, and you get a basis here. So this is definitely surjective. Okay? That's all I care. But this tells me that this guy is 0. Okay? So now we obtain that this is 0, and I want to say that the fact that this is 0 says that this is algebraic. Okay? What I promised at the beginning is algebraic if and only if the modular differential is 0. So let's look. Now we use the previous implication. Okay? And we already know by the previous implication that the dimension of the modular differential of K0 over K, okay, is the transcendent degree. No, sorry, of big K over K0 over K is the transcendent degree. Because this works in general. This already told you, every time you have a transcendental basis, this is a basis. So in particular, it tells you what the transcendent degree is. This implication is enough to tell you the transcendent degree. So it tells me the transcendent degree of this is exactly the dimension of this. But this dimension is 0, so that's algebraic. Yeah, so notice that actually this is just a consequence of this direction. Okay, that's all you need for that. Because if you have a basis, you get a basis, so it tells you the dimension. Okay, so now I'm not completely done because I just know that this is algebraic. It's mostly done. How can I prove? So I know that this is algebraic. What does it tell me? It tells me that U generates. I don't still know that U is linearly independent. Okay? So I have to show that U is linearly independent to have a transcendent basis. So we are not completely done. Remember the first part of the theorem before, number 1. If I have a generating set and a linearly independent set, I can find a basis in between. So I can always find somebody inside U, in theory somebody here, Ku prime, such that this one is really a basis, okay? So I can find U prime inside U because that's generating. So just take off the element that you don't need. So I can find U prime inside U such that U prime is a transcendent basis of K over little k. Now we better show they are the same, because we have to prove U is a transcendent basis. And now we apply again this part to U prime. So applying, twice I apply this part to U prime, we get that dxi with xi nu prime is a k basis of the modulo differential. But this was a k basis by assumption, so they have to be the same. Okay? Because a basis has the same number of elements, so this is containing here, so they have to be the same. Okay, so this does the part I wanted to show you. In particular, you can notice that the proof does prove that to detect an algebraic extension, just this one does it. To detect an algebraic extension, you just have to prove that the modular differential is 0. Okay. I'm passing to the another section, which is the ramification locus. Okay, so I want to give you a minute to digest this, and now I go to the ramification locus. I don't know how I'm doing with time. I already did an hour, that's bad. I'm not going to really, so I think I'll do the singular locus next time, and then I'll talk a little bit about the difference. But I think, guys,
Only 40 minutes,
sorry? Yeah, I have 40 minutes, but.
No,
You have 15, not 15.
Oh, good, good. So I can do more. I was afraid I would already pass an hour. Oh, that's good. So that's good. That's better. Much better. I still keep the sequence here because I'll need them. And by the fourth lecture, so this lecture I still want to give you every proof. Okay? But by the next lecture, I will have to cut through because I want to get to some results that usually you don't see. So because of that, I'll don't prove some theorem. I'll tell you this is the proof, but you'll find the proof in the notes. Okay? I may tell you what are the main ingredients, but the proof is going to be in the notes. Just that I can explain you at least the importance of what is in the notes. Okay? So, but today I still want to go through everything. So let's talk about the ramification locus. Again, I assume that the characteristic is 0. All this result holds in characteristic P, actually. So you have to be careful. It's not that there are results of characteristic 0. They are all results in characteristic P as well. The only problem is assume the field to be perfect, okay? Like this one is still true. You just need the extension to be separable. And that this just says every extension, the transcendent degree, the rank of the modular differential for any field extension is the transcendent degree, because we are in characteristic 0. So in general, you would say for any separable extension, the dimension of the modular differential is the transcendent degree. So if you're interested in characteristic P, you can prove the same thing, okay? But you need the separability. But we assume characteristic 0, so we always have it. And the same thing, and what I proved now about the ramification locus, everything goes through. You just have to assume that the field is perfect if you're in characteristic P. Okay, so now, I want to recall one thing that I'll need. So recall that, so this is called ramification locus. This is this section. So recall that the coefficient field of any local ring, remember that you can always denote a local ring with a triple. M is the maximal ideal, and the last guy, K, is the residual field, okay, R over M. So if I am in this situation, if I am in local ring, what is the coefficient field for any local ring? Is a subfield of R that maps isomorphically to K, to big K. So there's a field of R, let me call it little k, there's a subfield little k of R, such that K very isomorphic. Okay? All right. Now, a coefficient field does not always exist. We would be very happy if it did, but it doesn't, unfortunately. But if you have a complete ring, then it always exists. So, obviously in characteristic 0. We are in characteristic 0. Yes?
Might it be safer to say a coefficient field? Since it
A coefficient field. Sure, you can have a lot. So a coefficient field. That's much better. Sorry. So any complete ring and we remember we are in characteristic 0 as a coefficient field. Which theorem is this? Cohen structure theorem, remember? Okay, for example. So now, let me tell you the last thing, notation, this is just notation. Nu, we denote the minimal number of generator. Of any module, okay? And this is possible because it's well defined because we are in a local ring, okay? All right, and now of any finite R module. And now the last notation, so this is new, and this symbol again, in case you have not seen it, I think everybody did, but the embedding dimension. The embedding dimension of a ring is simply the number of generator of its maximal ideal. Okay? Clear? Okay. Okay, so now we're gonna, we have to define the ramification locus. But before I define the ramification locus, I'm going to actually describe the number of generator of the modular differential. So let me take this. So these are just notation. And now Okay. It's actually quite, it's not difficult, this theorem, at all. And it's an application of the conormal sequence, and you see that it's not difficult. So you have a local ring. This is the residue field, and assume that is a local K algebra. So there is a small k, essentially of finite type. Over little k. Okay? And then what we claim is that the number of generator of the modulo differential of R over K is the embedding dimension of R plus the transcendent degree of the residue field over little k. Okay? So this is what we came. We want to compute the number of generators. Okay, the minimal number of generators. This is an R module, as a finite R module. We can compute the number of generators. So how do we prove this? As I said, this is going to be not difficult. It's just an application directly of the conormal sequence. So I'm going to consider R over M squared. I don't know if anybody understands why I want to consider this ring. The reason is because this ring is complete, is thematically complete. Okay? Right? So this ring is complete, so it has a coefficient field. All right? So let me call it, no, I don't call it, which implies this ring is local and complete respect to the maximal ideal, hence it has a coefficient field. Containing K. And because we are in characteristic 0, so it's separable, this tells us that, and this is actually equivalent, if you want, this is really equivalent, that the natural projection, okay, has a right inverse, as a map of K algebra. Remember, this is big K. So here you are really using characteristic 0 very much, both for the coefficient field and both for this equivalence. Okay? If you don't think about the situation something like this is a K algebra, so you have this. This is the residue field that contains K, and this is an equality. But if it's complete, you also have an embedding of K inside R. So you can go backwards, okay? So this is the idea. So K embeds in R. Okay? That's a coefficient field. It's isomorphic to the residual field. Okay, so now this should remind you something. It should remind you this condition. So this tells me that the conormal sequence is split exact. So the conormal sequence is exact. Okay? And now remember, in our case, M is I. Okay? So you have M over M squared. And what we call T is simply big K. So you have goes in big K tensor over R with omega K of R. And this goes to omega K of small k and goes to 0. Okay? And now,
I
yes? now apply NAC. Nakayama's lemma give you the result. The number of generator of the modular differential is exactly this. That's how you get the number of generator. You have to tensor with the residual field, okay? And this is the minimal number of generator of m over m squared, which is the embedding codimension. And this is the number of generator of this, which is, this is a free module, so it's the dimension over k, which is the transcendent degree. So just apply Nakayama's lemma. These are vector spaces. The dimension is additive. The dimension of this is the transcendent degree. So this is the transcendent degree. This guy is exactly the number of generator of omega. And this guy is the embedding dimension of R. Okay? That's it. Okay, now we have an important corollary of this theorem, which is due to Berger and Kunz. And that takes you really to the ramification locus. So let me do the corollary of this theorem. Yes?
Is the right inverse specified just in inclusion of k?
Sorry? Yes. Yeah. So, Berger-Kunz. Again, in the same situation we were before, but I have this one, okay, and then this other. So I have two local rings, okay? And I assume that this is a local map. So what does it mean to have a local map? Means that the maximal ideal of this goes to finish in the maximal ideal of this, okay, via the map. Okay, so this is a local map, and this, we assume also that making R essentially a finite type over A. Clearly, any map of rings makes R an algebra, but we want more, okay? So it's a localization of a finite algebra, okay? So now, what we want to claim, and as I said, this is a direct corollary of this, is that the number of generator of the modular differential, now of R over A, not over K, okay, is the number of generator of M over Rn. So this is the image of the maximal ideal of A to R, okay, plus the transcendent degree of one residual field over the other. Okay? So how we're going to do this proof, we want to apply this one. So to apply this one, we want to go to a K algebra, essentially a finite type, and actually it's going to be easy because you see you have this, R is an algebra over A. I'm going to tensor all this situation with little k over A. And if you tensor with little k, what do you get? I get A tensor with little k is k, okay? And R tensor with little k with A is exactly R over NR. Okay? Remember, k is R over A over N. Okay? So I just tensor this with this, and I get this situation. And now I apply, and this makes still this ring essentially a finite type over K. And now you are here. You are in a local K-algebra essential for n type over K. Let's apply this one. It tells me the number of generator of omega of R over NR over little k is equal the embedding dimension, so the minimal number of generator of the maximal ideal of this, which is M on NR, okay, plus the transcendent degree of the residue field, of K over K, which are the same K over K. So it looks really very much like this. What's the difference? Here I have the number of generator of this module. I want the number of generator of this module. So I have to show that these two are the same. And then we are done. I'm going to leave this because we used it, and I'm going to prove under this. So you can check that this was really the same statement. So now I have to show that the number of generator of omega AR is the same as the number of generator of omega over little k of R over NR. Okay? So this is what I have to show. And now you can either use the conormal sequence again, or you can use the way that we show that you compute the modular differential of a quotient, because this is again a quotient. Okay? So how do I compute? I always like that one. So the number of k over Rn, I'm going to describe this guy. This is the modular differential of a quotient, and we know how to do it using the modular differential of R. Is, first of all, notice something. Here, I'm fixing k, but I'm going modulo Rn, so I'm really fixing A, because k is A over n. So this is the same as this guy. Because I fix k, but I'm killing n, so n are also constant. Okay? And now, this, I want to use the quotient. So it's the modular differential of A over R. And now remember, how do I compute it? Then I have to go modulo the image, IDS plus SDI, the formula. So this case is RDN, n is the maximal ideal, plus n omega. This is the usual formula for a quotient. Okay? It's the modular differential of S modulo SDI plus IDS. And now, what's happened? Guys, dn is 0, because these are constant in A. So this goes away. So this is simply omega of AR modulo n omega AR, which is omega AR tensor K. And then I can just compute the number of generator this way. So the number of generator is exactly the same. Okay, guys. So now I can, now that I have this two statement, that's all I need, so I'm going to erase the proof. This statement is what I need, not the other, this one, but I leave the other because it's interesting. And this is the statement I need. I can give you the definition of what it means to be unramified. So again, like here, you have same situation, a local map. Okay? And with the same thing, with R essentially of finite type over A. So exactly the situation of this theorem, same assumption. Okay? And you look at the extension of residue field. Okay, this is my extension of residue field. Then, what does it mean that R is ramified? It means that, first of all, M is obtained from N. So you get the whole maximal ideal just pushing this little n over. Okay? And this extension is algebraic. Usually you would say separable algebraic, but in our case, always separable. So now let's go look back to this. What does it tell me that is ramified? So the transcendent degree goes away. And what about this? It's 0. So you have 0 plus 0. So this tells me that this has 0 generator. So this guy is 0. So it's a ramified if and only if the modular differential is 0. Okay? Otherwise, you call it ramified. So the corollary of this theorem of Berger and Kunz tell me immediately that R is a ramified if and only if over A, if and only if the modular differential is 0. Okay? That's immediately what you get from Berger and Kunz. Okay, now we want to define the ramification locus or branch locus. Okay? So let me define the ramification locus. You can call it two ways. You can call it RAM, like I always call it. And lots of people also call it branch, because it's also the branch locus. So the ramification locus or branch locus is the set of Q in the spec R, so of prime, such that RQ is ramified over A, and now I cannot localize A Q, but I localize a Q intersect A. Okay, the contraction of Q to A, which is obviously prime. So all the prime where this is ramified makes the ramification locus. So this is called the ramification locus. Okay, obviously of R over A. And now what does this theorem tell us? But remember one thing, not only R is ramified over this, but the modular differential localizes. Okay, so this tells me that the ramification locus is completely determined by the vanishing of the modular differential. Okay, so this tells me that, so to write this well, which is very important, to write this well, I have to remind you a homework that I hope you did yesterday because it's very important, or if you didn't do yesterday, you did in your algebra classes. This is about fitting ideals. Remember that in this case, R is essentially a finite type over A, so the modular differential is finitely presented by the Jacobian matrix. So I can understand the vanishing of the modular differential via its presentation matrix. Okay? And how do you do that? How do you call that? So you have this situation. You have a module finitely presented by this matrix phi, and then you define the fitting ideal, which they don't depend absolutely on the presentation matrix, but only on the module, so that's why they're good. They are an invariant, but they are, you can compute it in terms of ideal of minors. They are the n minus I minors of phi. But you can take any phi you want, okay? That's a beautiful thing of the fitting ideal, they're invariant. And they are an increasing chain of ideals. So uniquely determined by M. And the V of this fitting is exactly the element in spec R where the module has at least I generator. So bigger than equal than I plus 1. Strictly bigger than I generator. So the minimal number of generator of the module, maybe you cannot read this. So I hope you have done this in the homework. And now, in particular, if you look at fitting 0, which is the ideal of maximal minor, this gives me the support of the module. Because the module has to have at least one generator. So it's non-zero. You know? And this, again, in the homework, is the same as V of the annihilator of M. Okay? That's actually the definition of the support, or you can prove that these are equivalent. I mean, you did this in algebra in any basic classes. And now I want to define one of the main subjects that should have been this class about, and obviously it's not because I never get to it, is the difference. And this is the first of the three difference, the Kähler difference, which is actually the easier to define, the easier to compute, but the worst behaved of the three. That's why we are free. Because they all give you the ramification loci. That's what I'm going to prove, that this gives you the ramification loci. But, you know, one is very algebraically well behaved, but is only defined in special situation. It needs a lot of assumption. This is defined always when omega is finitely presented. And the middle one has better property, okay, is also sometimes easier to compute, but not as easy as this. And on the other end, you know, it is all defined more in general, but the best one in terms of property is the last one. So next time, I'm sure on Friday I talk about them much more. Okay, but this is the first one. So is the Kähler different? And so you are in this situation, okay, where the modular differential is finitely presented. And then the Kähler different, I mean, this should be a D, a script D. I don't know how to do it. Maybe I just write it. This should be a D, though, a beautiful kind of D. So I'll make it like this. In the notes is nice, it's mafrac D. Imagine that it's mafrac D. So because it stays for different. And the K stays for Kähler. So the Kähler different of R over A. So the K doesn't stay for a K residual field. It stays for Kähler. The Kähler different of R over A of this extension is the zero fitting ideal of the modular differential. So really the maximal minor of the Jacobian matrix. Okay? All right. So this is what this guy is. So very easy to compute. Once you have the presentation of, you compute the Kähler different right away. And now the corollary of this theorem, the corollary of star, and the fact that the modular differential localize is immediately that the ramification loci, locus, is the support of the modular differential and is a closed set and is V of the Kähler difference. So the importance of the Kähler difference is exactly that it captures the ramification locus. It defines the ramification locus. Okay? Now I'm going to, before talk about the singular locus, I want to do 2 examples to just give you an idea of what the ramification locus look like, what are we talking about. And with 2 examples, I don't compute the Kähler difference because you're supposed to compute it as homework. So, if you cannot compute it, math helps you. It's actually not difficult. So, but let me do with 2 examples, and then I will. By the way, you see that in my notes, at the end of the notes, you didn't get all the notes, but at the end of the notes, you'll find an acknowledgement to Bernd Ulrich, because I learned all this from him, and he shared with me his notes, which are extremely well done. Unfortunately, he never wants to publish them, so at least we can publish this in a book, and and it's really thanks to him that we have all this treatment, which is very difficult to find in books, actually. So let me show you an example now. So example 1. And I think these were part of 2 homeworks that you had. First, you take A to be Z, and instead your ring R will simply the Gaussian integers, Z of I, which is obviously a finite type, is Z of X over X squared plus 1. Okay? And you should have computed the modular differential. Okay? You should know that the modular differential of R over A, okay, is simply, if you did it correctly, Zi modulo 2i, or if you want, is isomorphic to R over 2r. Okay? And this you should have done in the homework. Okay? Hopefully you did it. And then immediately, by the definition of the Kähler difference, this is presented by 2, so if you have a matrix with 1 entry, the determinant is that entry. So the Kähler difference of this guy is simply 2. The prime defined by 2, okay? And now, there's not a prime, but it's 2r. It's not a prime, sorry. And now what is the ramification locus? The ramification locus, if we use our definition, is V of 2r, and now we have to look at the primary decomposition, and this is simply given by 1 plus I. Okay? And now, so this should be all computed by your homework. And now let's see if this makes sense, because we all have studied the prime ideal of Zi. Okay? This is studied actually as an undergraduate as well, so I'm sure that you all studied undergraduate. So let's see if this is true. Let us check with our knowledge. So what do we know about the spectrum of Zi? What do we know about the prime of Zi? But we know that the prime of Zi arises in the following way. You have to look at the prime element in R, and if P is a prime congruent to 3 modulo 4, if you remember, I'm sure you have done this, then what do you get? That P is a prime element in R. Where is the razor as usual there? One is there, the other I don't know, maybe it's in the floor. Yes, in the floor as usual. So this is true if and only if. So this is obviously ramified because this stays prime. Okay? And now, so P is any prime number. So P is a prime in Z, and it stays a prime in R. Okay? And then you have other two situations since we're looking modulo 4. What are the other two situations? P could be congruent to 1, modulo 4, or since P is prime, P could be 2. That's the only other situation, because that's the only even prime. So you have free situation. And what's happening in this free situation? So this is remain prime. This is not prime in R. However, there are two prime lying over in R. Okay? And because this decompose as a square plus b square, you can write it like this, which is a plus ib and a minus aib. And both of these are prime in R. So there are two primes lying over. So this is a ramified. And then you get the last situation where P is congruent to 1 plus I square, and this guy is prime. So this is the ramified one, because you have this multiplicity, 2 prime lying over that. Okay? So it doesn't split off. It's not prime, but there is a prime, a double prime over that. Okay? Here I should write a plus ib, a minus ib primes in R. Okay, let's look another example which is more geometric. Again, it should be you should have done it in the homework. So let's see the more geometric example. So I have A is a polynomial ring over a field in one variable, and then R is a polynomial ring in two variables, but then since I wanted, I want to go modulo x minus y minus 1 square. Okay? Right? So now, what is I want to compute again the branch locus, okay? And in this case, you have this situation. So this is the spec of A, and the spec of R, this is a parabola, and the spec of R is here, and over every prime here, you have 2 primes. The only problem is here, and this is going to be the ramification locus, okay? And in fact, if you have proven the homework, you should see that the Kähler difference in this case is exactly this one, which corresponds to the origin of the parabola. Okay? All right, I have only 10 minutes, so in the next 10 minutes, I want to start a singular locus, okay? And at least I want to start, because otherwise next time I can do anything. And what I'm going to prove now is the Jacobian Criterion. Okay? And then next time I do much more. I want to generalize the Jacobian Criterion to prove the purity of the branch locus, to show you that to check that something is ramified, you just have to check in codimension 1. That's a very famous theorem called the purity of the branch locus. And my goal is to prove that next time. So I have to have a lots of generalization of the Jacobian criterion due to Lippmann to get to that. So I will start, And also it's very important because it tells you how the modular differential, here we see that the modular differential gives you lots of geometric information, tells you the ramified locus, and now we show that the modular differential tells you the singular locus. So the modular differential has enormous information about your ring. So it's obviously very important to study. So now we talk about the singular locus. So here I have to put singular. Locus. Okay. So, first remember, in case you don't remember, then the number of generator of a module is always bigger than equal than the rank. And equality means M is free, is equivalent. And this is easy to see because the number of generator can only go down, okay, when you localize. And that's why you have this direction. And the quality is also easy to see because to prove that something is linearly independent, you only have to prove it at associated prime. Okay? Here I should say that R is a domain, otherwise, I mean, cannot even talk about rank in general. I mean, I want to assume that R is a domain. Okay? And then to prove that something is a set is linearly independent, so to prove that you have a freeness, you just have to show it associated prime. Okay, but that means exactly when you compute the rank. Okay, and now remember also, again, in a domain, so you have R as a local extension of local domain. Let me actually write it like this, like I wrote before. I want to do it like this. So again, a local extension, local map. Same situation as before, essentially a finite type, okay? And domains, essentially a finite type, same kind of thing, okay? Everything the same as before. And on top, I want to assume that R is Noetherian and universally catenary. Do I want, yeah. Then what do I get? I get that the dimension, okay, A, not R, A should be Noetherian and universally catenary, this guy. So, which is okay, then everything fine. So what do you get? That the dimension of R is the dimension of A plus the transcendent degree of R over A. And remember, this just means the transcendent degree of the quotient field of R over the quotient field of A, okay, minus the transcendent degree of M over N. No, so, sorry, of big K over little k. Okay, this is the dimension formula. So I'm not going to prove it, but I assume you have done it, okay? I'm sure all of you have done it. And I'll need it. Okay? Hopefully all of you have done it, so all of you know it. And now we are ready for the Jacobian criterion. So if this is clear, you can define transcendent degree when you have two domains, and this just means the quotient field of this over the quotient field of this. Because the quotient ring are fields, since they are domain. Yeah. From until the end, it's always characteristic 0. I never assume characteristic P anymore. I mean, I never have characteristic P, never. I just told you what can you do when you have a characteristic P. So now we assume that you have RMBK is a local K algebra, essentially of finite type over K over little k. Okay? And we write D for the dimension of R, the Krull dimension, okay, plus the transcendent degree of big K, the residue field, over the little k. Okay, and now we want to prove that the following are equivalent. All right, R is a regular ring. If you want, the singular locus is empty, because second, the modular differential is free of rank D and third, the fitting ideal of the defitting ideal of the modular differential, okay, which is the minor, n minus d minor of phi of the Jacobian matrix, is exactly R, is the whole ring. So in this case, so these are not the maximal minor, are the n minus d minor, okay? In this case, D, this D turns out to be, so this is also a claim that we have to prove, that if this is the case, under this assumption, this is the transcendent degree of L over K, where L, this is small k, L is the quotient field. Okay, so this is of R. Okay, so now I want to prove this, and I have only 2 minutes, but the proof is not difficult, so it should be coming quite easy. I'm going to use the two things I wrote in the board. I'm going to use this characterization and this fact. So this will give me the freeness, this. Where? That this number is actually transcendent degree of the quotient field of R over little k. But that's in this assumption. If one of this is verified, then D is exactly that number. D will turn out to be the rank, okay, and that's why, of the modular differential. So, like we had before, when it's free, okay? As you see here, it's free of rank D. And now next time, we are going to take off this. That's going to be the first generalization. But if it's free, it has to be of that rank. So we're going to just show that it's regular if and only if it's free, without asking for the rank. So now, but we'll do it next time. So first of all, 1 implies 2 and also implies the red and red all together. So we are going to use the dimension formula. So this dimension formula. And this dimension formula tells you immediately that the dimension of R is the transcendent degree of L over K minus the transcendent degree of K over K. Because A in this case is a field, so this dimension is 0. Okay? So you just get this difference. And remember, this I told you is just the quotient of this, so L over this, the transcendent degree of the quotient. So it's exactly this. Remember that my A is little k in this case. Okay? So that's the thing. That's why you get just this. And now, so in particular, look at this. D is this number. Because it's the sum of the two. So we get red right away. Red is for free from the dimension formula. And now let's prove the other, that this is free. But it's just an equality of ranks. The ranks of omega is less than equal than the number of generator of omega, as I told you before. But this is, we computed it, is the embedding dimension of R plus the transcendent degree. That's what we did before. We compute the number of generator. And now this one, since R is regular, is the dimension of R. So here I use my assumption. R is regular, which means that the minimal number of generator is a regular sequence. So the embedding dimension is the dimension. Okay? And this is D, which is the transcendent degree of L over K. But the transcendent degree, again, by the formula, is the dimension over L of omega K over L. Okay, is the rank. And this is the same as the dimension of L tensor omega R over K, but this is exactly the rank. So you get equality throughout, and this gives us freeness. Freeness of this rank. Okay, and now we're really done. Why we are done? Because the rest of the, so we proved 1 implies 2, and 2 implies 3 is clear because this module is free. Okay? And this is the presentation matrix. So that's clear, because you cannot have any generator, okay, past this. And now let's look at 3 implies 1. So we have to prove that if the fitting is R, then this is regular. But that's going to be really very, very easy. So, I mean, somehow I should give it as a homework, but let me write it down. Sorry if I take 2 minutes more, but then you don't have to do it as homework. So we are assuming that the fitting, the D-fitting ideal is R. So what does this tell us? The D-fitting ideals, by definition, give you the place where the number of generator is bigger than D. So since this is R, the number of generator of this module is always less than equal than D. Okay? But the embedding dimension of omega, okay, is, the rank is the embedding dimension, like we proved before, the minimal number of generator of this guy is the embedding dimension of R plus the transcendent degree. Remember? We use it, and then we had Berger and Kunz. But that implies that D is the dimension of R plus the transcendent degree of K over K, okay? And now, no, actually, this doesn't imply. We assume this, I suppose. We already proved that. And now what do we have? We have that the number of generator of this guy is less than equal than D, but this tells you that the embedding dimension has to be less than equal than the dimension of R. So this tells you this, so which implies and this can only be if equality holds. So R is regular. Thank you, guys. Remember, this was D. D was this number. And so you have this is less than equal than this number. Thank you. Sorry, I will never do this again. Maybe tomorrow I subtract 6 minutes. I should not, I don't like that. But it was good to finish here so I can start with generalization of Jacobian and talk about singular locus tomorrow.
Thank you very much for your talk. Are there any questions?
There is a version of higher differential like the principal part. So if you have, is it true that if the model of principal part under the same hypothesis equal to 0 is equivalent to ramified?
I don't know. Maybe it's true, but I never thought about it. So I have to think about it. That's an interesting question. So there are lots of generalization of this in many directions, so yeah. And remember, there is a module of higher differentials. That gives a lots of good stuff. Okay, guys.
Okay, so it's time for lunch.